Hi. This is the fourth lesson for the best practices for robust and reproducible neuroimaging meta-analysis for the OHBM 2023. I have no disclosure for this course. And I'm going to talk after Alejandro, Kendra, and Katie on the pitfalls and reproducibility aspect of meta-analysis. So the goals for these presentations are first to restate some of the statistical issues that we have to deal with. Second, I will go into a specific pitfall, which is the reverse inference question, and then possibly have some thoughts on what are the good long-term mitigating strategies to help mend for some of those pitfalls. I'd like to start with this slide that has two components. One is showing that there is a huge number of publications every year, and that huge number of publications is not necessarily helping the science to move forward quickly. And the second aspect of the background aspect is that we are still struggling in life sciences to have good and solid individual studies, and that's what the Lancet is naming as the 5 sigma of health and health sciences. And mostly that's because of small sample size, analytical flexibility, p-hacking aspect, statistical training, and so on. So I'd like to just remind everyone that this is the background we are in, a huge number of publications, and within that huge number of publications, not always a very good, solid results at the individual study level. And that's why, obviously, we want and need to do meta-analysis. So I'll go into some of the individual study statistical issues first. Going to small power, small effect sizes is one aspect. Witness curves, just defining what it is. P-hacking issues and fire draw effects would be my the 4 things. I will briefly remind everyone what they are. And before that, I would like to take an example of a meta-analysis in the field of looking at essential tremor and the involvement of the cerebellum in essential tremor, and looking at meta-analysis, the Rudis et al. Paper. And we actually designed and pre-registered a study with a good power, something like more than 85% of power, and a bunch of different possible pipelines and ways of analyzing data, and we basically did that well-powered study to check whether the results of the meta-analysis were sustained. And in fact, after looking at the different pipelines and different ways of computing the involvement of the cerebellum and the different structure of the cerebellum in essential tremor, we didn't find a very consistent result. We didn't find consistent results, which basically says if that meta-analysis is correct in terms of the way what they show is what they found, but it doesn't mean that that result of the meta-analysis is solid. And the reason is that probably the actual studies in that meta-analysis were themselves not well powered. So with a small sample size, and that's the problem that we want to deal with in that 4th lecture. So small power, small effect sizes. I would like to illustrate the problem with a very classic figure, classic in the way that I use them. I use it classically, which shows you the x-axis, the term of publication, and the y-axis is the effect size of the association of the BDNF variant with the hippocampal volume. And the size of the cohort, or the sample size, is reflected by the size of the little circles that you see. You see early on small circles, so small sample sizes, and effect sizes that are a bit variable, but often quite high. And then later on, later publication with larger sample sizes, that effect size is going down to a point where it's not clear whether it's going to be non-zero at all. Like it might be like there may be no effect sizes or noticeable effect sizes of this association. So if you were to do meta-analysis on the early years, you would probably find something significant across all those studies. And if you were to do this meta-analysis on the later year, probably that effect would be much smaller or possibly not significant. And that's the problem, like, that the quality and the robustness of the individual studies is actually should be taken into account in some ways in meta-analysis, and we don't have yet a good way of doing that. We can take, of course, the sample size into account, but that's about it. And just to remind everyone that in brain imaging, the effect sizes are pretty small, and that's the Marek et al. Paper, fairly recent paper, showing that you actually need thousands of individuals and participants in the study to actually describe some effects between cortical thickness and cognitive ability or psychopathology, either in the anatomical or the functional world. So that's the world we live in, and obviously some studies have much higher effect sizes, so it's not a general remark, but I think we can say safely that many studies have small effect sizes, and we have to think about how we deal with that. So the small effect sizes and the small sample size, the small number of participants in the study lead to a small PPV. PPV, what is PPV? It's the positive predictive value, and it's defined as the probability that you have actually an effect, knowing that you have a significant test. So you find a significant test, but the interesting question is not about that test itself or the effect that you find that there's a significant effect. It's about the hypothesis. Is the hypothesis that there is something going on in that region or that study? Is that hypothesis going to be true? What is the probability that hypothesis is true, given that you have a significant effect? And you can find fairly low PPV in as soon as you have a bit of p-hacking. I will talk about p-hacking right away, but also low-powered study, and that's the problem. That even if we find something significant, the probability that you actually have a result is actually not that great. Often. So another aspect of the studies I think is interesting to notice and to at least know the name of is the Winner's curse, and the Winner's curse is a very kind of a basic effect. Any statistical thresholding will have that effect. So association passing predetermined threshold of statistical significance tend to overestimate the size of the effect. So if by mathematically, if you say, hey, I'm going to report only the things that are significant above a threshold, you are overestimating the effect of the size of the effect. So when does it occur? When there is a predefined threshold, so p 0.05 classically, alpha equal 0.05 classically, small sample size, and stringent type 1 error, for instance, when you do multiple comparison and you have to threshold very high to correct for those things. So those aspects will actually inflate the effect size that you report. And last but not least, the p-hacking or analytical flexibility aspect. I've put that in one box. There are differences a bit, but it's a very classical problem that has been described in Simonson's 2011. That basically, you try different models, try different ways of analyzing the data, and then you only report the ones that are significant. I think it's an important message that mostly it's not done in it's like in the knowing that this is a wrong way of doing it. So it's mostly done I must have I have a better model, I have a better way of analyzing the data, and that better way is going to give me a significant p-value. So it's a problem of education, and it's a problem of and as soon as you can, I would really recommend that you use pre-registration for not having that nefarious effect of p-hacking, which is inflating the type 1 error risk, inflating the risk of false positive in your results. There are actually tests to know whether a field, a subfield of science has done some p-hacking, is in general doing p-hacking, and so I would recommend to if you're doing a meta-analysis in some subfield, maybe you'd be interested in looking at those tests to see whether there is false positive likelihood, a greater likelihood of false positive in the in vitro studies. The fire drawer effect is almost like the social aspect of the winner's curse in some ways. It's the fact that if your threshold, if your result is not significant at your type 1 threshold, let's 0.25 or whatever, you're unlikely to publish the result. Or even if you want, editors or journals are unlikely to accept easily a non-significant result report. So that effect has been shown, for a long time, like 1979, and yet we're still, I think, in the phase where non-significant results are basically very poorly published or not published. And if you look at the z-value reported in Medline, you see that interesting distribution that around 0, there's very much less z-value reported around 0, because you only report the significant positive or negative z-value. But obviously the actual distribution of the z-values is you should complete that distribution, and it's definitely doesn't have this hole. It's just like we're not reporting all those z-values that are not significant. So what are the consequences? First, small power, it does bias the effect size. Winner's curse effect also biases the effect size, so you always report higher effect sizes than the actual ones. P-hacking is more on the uncontrolled type 1 error, so you put more false positive than you expect, so you report things that are in some sense. P-hacking actually biases the effect size in the other direction, possibly. You may report effect size that are smaller. And fire drawer effect also biases the effect size in the positive direction, because you can't average with things that are non-significant. You're actually basing again towards a larger effect size. So I think in general, the literature will have much larger effect sizes than the true ones. So the individual result biases will be reflected in those meta-analyses. So when we do a meta-analysis, we will see inflated, we will report a meta result that is inflated in effect size. So to summarize a little bit and to capture that problem, each individual study is low powered, and the aggregation is not giving more information. So if the problem is that we have very low power individual studies, I don't think the aggregation or the meta-analysis of those things will help to solidify. They will help a little bit, of course, but not that much. And also the other aspect is that if too few studies are included in a meta-analysis, then we don't know whether it's an n which is very small at the level of the study. So how many is too few? How many is too low powered or not too low powered? I think it's a bit of a trade-off, like a bit like in a mixed effect model, where you have a lot of information in those studies, but you also want to capture the meta-analysis aspect, which is the across study effect. The last thing I want to say is that, all the coordinate-based meta-analysis and actually also the others, they don't take into account the file draw effect. So we don't know how many studies on that specific topic have been done and not published. And I think that's one of the biggest problem that I have with currently with the literature on how to do properly meta-analysis. Right, switching gears and now talking to another specific caveat that has been described in the literature that I want you to know about is the reverse inference problem. And the reverse inference problem is really trying to look at the probability of a mental state of a particular subject or group of subjects given the activation. And that's a much harder problem than the looking at the probability of the activation given a certain mental state, the usual thing that we do with fMRI. And to compute that probability, which is not the same as this one, we need the other probability of the mental state themselves, probability of the activation that can be expanded and computed this way, which is not that easy. Like you have to think of how you compute those things. So predicting the mental state process from activation pattern relies on the fact that the brain pattern is specific to a mental state. And the question is whether there are regions that are selectively activated by only one mental state. If I see that region, can I infer that that participant is doing Y? If I see this region X, do I know that that participant is very likely that that participant was doing Y? And the initial reverse inference of neurosynth that is being widely used was actually an association test. And that's led to these debates between some authors and Yarkoni and Tagliarconi, that some of those authors, were using neurosynth to say, hey, the dorsal anterior cingulate is actually very selective for pain, and Tal rightly, I think, corrected that is actually not the case. First of all, there are problems of the position of the DSEC, where it is exactly and how it's defined. Is it defined functionally, and if it's defined functionally, it should be defined with a reverse inference perspective. And then also the claim has to be more than the original authors of that claim were looking at just the comparison of pain with three other categories, amongst many more. And the fact that pain term shows the stronger z-score when indeed the dorsal anterior cingulate does not imply this selectivity of the dorsal anterior cingulate. So those are the caveats for reverse inference that were elicited, were noted in that. In that debate that happened, I think, which was very interesting actually, and really useful for the community to see and understand how we do reverse inference and how we should be careful with reverse inference. And I think that's one of the fundamental aspects and problem is that there are a very large number of mental states that are not possibly always well studied and documented in our databases of neurosynth neurocurry databases. And also we have to be aware of what exactly is the computation done. If initially the reverse inference was actually an association test, I mean, you have to know how the association test is done to actually understand that it was not a reverse inference. So we have to be careful with the claims and also huge, very large data sets to estimate those probabilities. So conclusion, we absolutely need meta-analysis. More fundamentally, we need better individual analysis such that we can do better meta-analysis, better powered, more robust with respect to analytical flexibility. I think possibly even more fundamentally, we need to be able to publish non-significant results. I mean, that file draw effect is really tremendous in terms of how do we aggregate results across studies. If we don't see all those studies, we won't be able to actually do a reasonable job. And therefore, we probably need a better academic system for publishing, and that's something that hopefully will improve in the future. summary, I've talked about a number of statistical or publishing practices that affect results in individual studies and therefore meta-analysis studies. And I've talked about the specific caveat of large-scale meta-analysis, which is how to do and what the possibly issues of reverse inference claims. And on that, I will thank you for your attention and hope that you will have a very good meeting.